In the last video, we started with a brief introduction to the idea of fields when we realized that space was a thing and fields are properties of space. So I'd like to spend a bit of time just doing a little more careful job of thinking about what a field means to a physicist. If you're used to hearing the term in the context of math, this definition is different, although there is a little bit of overlap between them, so be careful. To a physicist, a field is a representation of any physically measurable quantity that can vary in space. And for our purposes, we can break these into scalar fields. These are where the physically measurable quantity can be represented by just a number. So as an example, if you look at a weather map and you look at a temperature map, so say, pardon my horrendous art here, but there you go. You go and look at some temperature map on a weather website or something like that, you'll often see that they draw in these bands, or they'll say the temperature in a particular band is between a certain value and a certain value. So what this amounts to is a recipe where I can look at a particular location, like let's say right there, and we might look at that and see that at that location we expect the temperature today to be 19 degrees Celsius. And then maybe a little further north, we might look and expect the high today to be 14 degrees Celsius. So what we're doing with this map is we can associate a position with a numerical quantity, in this case, the temperature. And temperature is just a number, so this is an example of a scalar field. For every single latitude and longitude coordinate, you can associate a temperature. We can also have vector fields, and there are also tensor fields, but you worry about those in grad school. In a vector field, here, let's steal the map. It'll be a lot easier. There we go. Put it down, say there. So an example of a vector map would be, for instance, if you look at a wind chart. Now I'm going to draw a wind chart the way a physicist would draw it rather than the way they actually draw them. So the way a physicist would draw a wind chart is at every reporting station, we would draw a vector representing the velocity of the wind there. So the longer the vector, the faster the wind is blowing at that location, and the direction of the vector arrow indicates the direction the wind is blowing. So this is a wind map here. And for instance, it's not necessarily going to be blowing the same everywhere. We might find that, say, over here, the wind is particularly calm. In that case, there'd be a short arrow there. Now, all this means is that at this reporting station right here where we drew the dot, the wind is blowing this fast in this direction. And maybe the direction is different somewhere else. You get the idea. Now, as a practical issue, if you actually draw longer vector arrows for greater wind speeds, the arrows tend to start lying all over each other. So in real wind maps, they have this system where they draw all these little flags on the end of lines to indicate how long the vector is without actually drawing longer vectors in order to declutter the map. But that's the idea. So for every location, you associate a vector, in this case, a velocity. So you might ask yourself, can we do something similar with the forces, for instance, or something like that? And the answer is sure. We can, let's do, as an example, the gravitational field. Now, just to make sure that people don't get all over me in the comments here, this is a little bit, this isn't quite exactly right. This is valid in what is called the weak field limit. It turns out that with gravity, space itself is the field, which makes gravity a little weird. But as long as you're not standing like next to neutron stars or black holes or something like that, you can employ what's called the weak field limit of Einstein's theory of general relativity and do the same kind of thing where we can associate a gravitational field with a particular point in space. So for instance here, let's imagine that we've got the sun right here. And we want to come up with some recipe that will tell us, if I put a rock somewhere, like let's say right here, how big will that force be? Well, we're in luck. We've got Einstein's theory of, we've got Newton's law of universal gravitation, which tells us that the gravitational force is equal to minus g times the big mass times the little mass over r squared, where r is the distance between the two, r hat. And the r hat is again here because since both m's are positive, this will be a positive quantity, but r hat means away from the sun. So let me just draw in an r hat here for us to keep straight. So we need it to be negative, so minus r hat points towards the sun. So there we go. That is our gravitational field strength. Now, I don't necessarily really, our gravitational force. I don't necessarily really have to have a rock there. I could imagine putting rocks in all sorts of different locations. I could say maybe put a rock here, and we know it'll feel a much larger gravitational force at that location, but it would be given by this exact same formula. Again, the minus r hat means towards mass of sun, mass of rock over r squared. What if I doubled the mass of the rock? Well, then I doubled all the forces. But in a certain sense, if I'm wanting to think about how the sun is influencing space, so remember in our model here of how gravity works in the weak field limit, we're saying the sun is influencing space and then space interacts with the rock. So to that end, what we can do is we can define what's called the local gravitational field vector. And we can define it as based on the effect that we would get if we put a rock somewhere. So what we want is we want to say, I imagine placing a test mass at some particular location. I figure out the force of gravity on that test mass, and then I divide the test mass back out. Then later, if I go put a real rock here, I can figure out the gravitational force by taking the mass of the rock and timesing by the field strength. So let's figure it out for the sun here. Our gravitational field vector will be minus G big M little m over m test over r squared, r hat. And then I will divide out the test mass. Cancel, cancel. And I am left with minus gm over r squared, r hat. Now, if I just wanted, so that gives me both the magnitude and the direction. So now if I plot the local gravitational field vector for the sun at any location, the minus r hat here means towards, and we see the closer I get, r will decrease, so the field strength will increase. So out over here somewhere, little g will be pretty small. Same, say, over here or over there or over there. But as I get closer, it'll get bigger, like so. And now, if I wanted to find the force that some actual rock would feel, I can just figure out what the gravitational field vector is at this location. Say the force that the rock would feel would be the mass of the rock I choose to put at that location times the gravitational field strength at that location. So why didn't we do this before? Well, the thing is with gravity, all the charges are positive. So you're not really worried about, oh, it's towards, if it's plus, and minus if it's away, or vice versa. The force always attracts. There are cases, if you're doing crazy things like launching satellites out to the outer solar system or something like that, where thinking about the gravitational field vector would be more useful. But those cases are fairly limited, and most of the time it would just be an added complication. But we can take a look at an example near the surface of the Earth. So let's say you are standing near on the surface of the Earth. So the Earth will have a radius of r sub Earth and a mass of m sub Earth. And we can think about dropping some rock near the surface of the Earth. I actually want it to be a lot closer than that. Something like that. I want this to be close enough. Think like, the center of U is basically 1 meter above the surface of the Earth. And the radius of the Earth is 6.37 million meters. So, an extra meter or so doesn't really matter much. So let's go and follow that through. So we'll call the distance from the center of the Earth to U just little r. And then we can figure out the gravitational force on U or a rock nearby or whatever. That would be equal to big M. Sorry, we can figure out the gravitational field strength since we've got that already. It would be equal to big G M over r squared. I'm dropping the minus sign here because I'm just working in magnitude now, and this minus sign is all about direction. So here, we're near the surface of the Earth, so instead of it being the sun, it's the mass of the Earth. Now, if you're talking basically anywhere that either you or a machine can breathe oxygen, it's not a big error to replace this distance from the center of the Earth to U with just plain the radius of the Earth. It'll change the answer by less than 1%. All right, so let's figure out what this value is. This will be 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. The mass of the Earth is 5.972 times 10 to the 24 kilograms. And the radius of the Earth is 6.371 times 10 to the 6 meters, and we'll need to square that. If you crunch that all through, what are you going to get? You get 9.8, but 9.8 what? Well, this meter here is going to get squared, and so that will cancel off both of those powers there. There's only one power of kilogram to cancel something there. So we are left with 9.8 newtons per kilogram. And this is really the correct way to express the gravitational field strength, because using the price analogy I was mentioning in the previous video, this tells me that if I have a 1 kilogram object near the surface of the Earth, it would feel 9.8 newtons of force. If I had a half kilogram object, it would feel 4.9 newtons. If I had a 2 kilogram object, it would feel 19.6 newtons, and so forth. So really, this is a gravitational field strength. Now, a lot of books do you the absolute opposite of a solid by calling this the acceleration due to gravity, which is only true if you are in free fall near the surface of the Earth. But the gravitational field is always there. So if you have a book sitting on top of a table, what's its acceleration? 0, because it's sitting on top of the table. But gravity is interacting with it, and it's interacting with it to the tune of its mass times 9.8 newtons per kilogram of force. So why do they get away with doing this for the free fall? Well, let's just follow this through. So let's say we are in free fall. And as a quick reminder, free fall means that if I draw a free body diagram, literally the only force is gravity. So we can go ahead and write Newton's second law for this. And we'll say that A is equal to F net over M. So this will be equal to the force of gravity over M, which will be mg over m. And blithely, we just go ahead and cancel these. But this is actually a bit of a subtlety why we're allowed to do this. Technically, this m here is a measure of the inertia of an object. So we call this the inertial mass. It says that this says how hard it is to change the motion of an object. On the other hand, this m here from mg, when we substitute in for the force of gravity, this is the gravitational mass. This says how hard gravity interacts with an object. If you think about it, these are actually two different physical quantities. Now, experiments have been done that showed that to within at least as good as a part per billion, maybe better, but the experiment's limited to a part per billion, these two masses are equal. So we go ahead and cancel them. And in fact, one way that you can start to come up with our current best theory of gravity, Einstein's theory of general relativity, is to assume their equality and follow through on what that means. But there's no particular reason why you would have to cancel them. Now, if this were the electric force, you would have a Q times an E up here, and nothing would be canceling. You'd be left with a Q over M. And we'll see that as we go on looking at what's called the cyclotron radius problem eventually. So this is where, so what we get is this equality. So then you ask yourself, well, I'm expecting meters per second squared for the acceleration, right? But we know this is newtons per kilogram over here would be the more correct way to describe it. Are these equal? And the answer is yes, they do have the same physical dimension. If I take a newton per kilogram, we remember the definition of a newton is a kilogram meter per second squared. That'll be divided by kilograms, and I am indeed left with meters per second squared. But really, if you want to be careful about it, when you write G near the surface of the Earth, you should write 9.8 newtons per kilogram. And then only if you wind up equating an acceleration to the gravitational field strength should you change that to meters per second squared, because these are different physical quantities that happen to have the same physical dimension. Now, usually this is something that when gravity is presented, we busily gloss all over because it doesn't really loom too large. All forces are attractive, all masses are positive. So it's something that tends to get swept under the rug a bit just because there's so many other fish to fry. All right. But with, as we saw in the previous video, with electric fields, here, because the electric charge can be both positive and negative, an electric force, saying that an electric force is equal to the charge times the electric field strength at some location. Now you're saying, hey, if it's positive, the force and the field are parallel, and if it's negative, they're anti-parallel. So let's say we have a positive charge here. We saw in the previous video that the electric field strength for any point charge was 1 over 4 pi epsilon naught q over r squared r hat. And remember, r hat just means away. So at this location right here, the electric field would point out. If I were to place a positive charge at this location, it would feel an electric force at that location pointing away. But by the same token, if I were to place a negative charge at that location, it would feel an electric force pulling it towards. So here, the field is a property of space. We don't know exactly how the fields work because we're still trying to figure out what space is beyond just merely saying it's a thing. But the field is a property of space. And so when I put a charge at this location, this charge is interacting with this location space. But the electric field at this point in space here was modified by the presence of this charge over here. So this charge influences this point in space. This point in space interacts with any charges that happen to pass through it. And the electric force will be parallel to the electric field if the charge at that location is positive, and anti-parallel to the field if the charge is negative. So because of this parallel anti-parallel thing, it becomes a lot more useful for us to go and use the electric field formalism. Alrighty, so in the next video we will go and take a look at some of this with numbers and start to take a look at the technique of studying limiting cases. Catch you in the next one.